I'm sorry again to miss Thursday's lecture. I hope you will forgive me. You know how busy we are. So last week there was a very important conference in Seoul, so I had to attend to the conference. Okay. Today I'm going to be talking about this topic, support vector machine, and actually, wait a minute. Support vector machine, and here I'm going to be talking about and also gradient descent. The two methods, the subtopics. And also this relates with linear classification. So there are three items, and I need to go over them rather quickly. So please ask questions. So who has heard about any of these topics? All familiar with these? So I can just... Okay, but there are many who haven't heard these things, so I'll try to... Now, so support vector machine. It's used for classification and regression. Okay, but it is most often talked about or discussed with regards to classification. Okay, so I'm going to be talking about SVM, support vector machine, in relation to classification. Okay, and so I went through this to see. So I have yellow dots and blue dots as shown here, and I would like to place a decision boundary, okay? And I define what a decision boundary is. Decision boundary is a set of points in the input space where it's where you cannot make a prediction. Okay? So if a point lied here, I would not be able to predict whether it's yellow or blue because they, so that's what decision boundary is. And if it lies above this line, then it's classified as yellow, and it will receive label 1. Label +1. And if it lies below the red line, it receives label -1. Okay? So yellow is +1 and blue are -1. And I mentioned this in my last lecture, it's possible that I can put there are many possible decision boundaries separating the yellow and the blue, as shown here. Okay, these are trained. But we don't know how it will perform on the test data, right? The important thing is how well it performs on the test data. This is only on training data. And the philosophy regards to support vector machine is to have a wide road centered around the decision boundary with equal width, such that the points don't lie on the road. They can lie on the edge of the road, but not within the road. Okay, so I want a really wide road. So, and that would depend on where the decision boundary is, right? Decision boundary would be the center of that road. Understand that? And the width of this road is called the margin. Okay, it's the margin. So let's assume that the line is can be represented by a linear equation as such. Okay? X here is multi-dimensional, but for this example here, X is two-dimension, theta will be two-dimension, and then there's a bias, equal to 0. So that's represented by the red line. Now, I asked you before, in last week's lecture, what will be the distance of this yellow point if I denote this as x1. Okay, x1. So this is x1 will be two-dimensional. It's two-dimensional. What will be this distance? That distance. If the red one had that equation. Can someone tell me? So let's go through this very quickly. Okay. So I'm just going to draw add a line. Theta transpose x plus theta naught. Okay. Now, which way is, so this is two dimensions. X will be x1, x2. This is for example. This vector theta, which, where is it pointing to in relation to this line? Think of theta naught equals 0. Think of theta naught, the bias is equal to 0. Where is theta pointing to? It's a vector, right? Theta will be theta 1, theta 2, right? Where is it pointing to? Assume that this is equal to 0. Where is theta pointing to? Theta will be pointing that way. Right? If theta equals 0, then you would have a line like this, and then all these points will be orthogonal to that theta. So theta transpose x would be 0, right? If it was there. But I have this bias, right? Non-zero bias, so it's shifted. Easy. Now, if I had a point like here, x, x star. Let's say x star. How far is x star from this line? How do you do that?
Peanut product.
Yeah, so what I would do is take a point here. Let's say a point here, and I'm going to call that. It's bad notation. I'm sorry about bad notation. Let's say I call this. Very bad notation. X1 and x2. X1 and x2, and I call that x. 0. Okay, so theta inner dot product is this vector x star minus x0. That will be this. That will be that thing right there, right? Inner dot. That's inner dot product. This is this vector. That will be that vector. That's inner dot product, right? And I don't know whether this is unit vector or not, right? So what I do is I divide this thing by theta like that. That will give me the distance. Now let's try to manipulate this just a little bit. That will be like one, and that will be like, I put this in theta transpose x star and theta transpose x0, right? And this will be that theta transpose x star. Now what is this value right here? It will be theta 0, right? Okay. So right here, when I go to here, what is that distance right here? That will be theta transpose x1 plus theta 0. There you go. Okay? That will be the distance. Now, so this is predicting, okay, so if it lies above this line, that this value, what would be the sign of this value? If it lies above the line, what would be the sign of this value? Positive. And I multiply with the ground truth label. Ground truth label is either what? Either +1 or -1, right? Y1 can be either -1 or +1. There you go. Okay, so if the prediction corresponds with the ground label, then what would this value be? What will be the sign of this value? Positive. If the prediction and the ground truth label are opposite, then this is what? -1. Okay? So the sign will tell you, the sign of this will tell you whether the prediction and ground truth are in accordance. If they're not, If it's misclassified, then it's minus 1. Minus, right? So, this is sine distance. It's sine distance, well, product of sine distance and label. And we call this the geometric margin. Okay, we call that the geometric margin. It says margin here, geometric margin. Okay, geometric margin. And I'm going to introduce another terminology, functional margin. Which is this theta times the geometric margin. It's the product. Product of the magnitude of the gradient and geometric margin. Okay, and we call that the functional margin. Okay, functional margin. So geometric margin and functional margin. New terminology for you too. Okay. This point, the point that's lying on the edge of the road, will have what? Will have functional margin equal to what? This point. This point. Functional margin is what? Functional margin equals what? No, so the yellow point, it's on the edge. What is the functional margin of that? 1. Okay? All the points that lie on the edge will have functional margin equal to 1. Let's just define it that way. Just define it that way. Okay? Understood? Okay? And there is a name. These points with functional margin equal to 1 are called, what do you think they will call? What do you think they are called? Yes, they are called support vectors. These are called support vectors. The support vectors, you can say it this way. Okay, so if I have decision boundary here, then the support vector is defined, right? If I have my decision boundary here, the support vectors are defined. These points are defined. Or I could say it the other way. These points, the support vectors, define this decision boundary. Right? Decision boundary defines the function, the support vectors. The support vectors define the decision boundary. What do you think is the minimum number of support vectors to define the decision boundary? Yeah, you need 3. So let me just reiterate. Support vector machine is a linear classifier. Okay? It's labeling it either +1 or -1. Okay? Also -1. And it's a linear classifier, so the decision boundary is a linear line. And it's putting the widest road, or it's a decision boundary with the largest geometric margin. Geometric margin. The geometric margin is the largest of all the classifiers. For all the classifiers that you define here, the geometric margin of this one, there are infinite number of the possible decision boundary. This particular one has the largest geometric margin. You could put the largest, the widest road between the two training data, 2 classes of training. Okay. Okay, now I'm going to do this. Everyone understood the philosophy of support vector machine? Now I'm going to. So, what's the next step? Define the philosophy. Now, what's the next step? So I'm given training data, and I want to find the support vector machine. What do I have to do? What do I have to do? I need to find what theta is. This is the whole. This line is defined by what? If I define this line, then I could get the support vectors, right? How is this line defined? It's the gradient and the bias. That defines this line. I need to find out how I can find this line, right? So how do I find this line? I need to set up a mathematical equation. And you said it right. And I'm going to define an optimization problem. Okay? So, let's look at this and check whether what I've said so far is correct and it's in accordance with this equation. Look at this. Let's just look at this first. What is this? Geometric margin being greater than C for I equals N. So how many training data do I have? N training data. I'm looking at all the geometric margin of each of the data, and I want that geometric margin to be greater than C. Right? That's what it's saying. Right? That's what that's saying. And what is my objective? I want to maximize C with respect to theta 0 and theta. Wow. That's exactly what I said. But formulated in a mathematical form. Yeah. Okay, good. Okay. So, I need to solve this. Okay? I need to solve this. But I'm going to just fudge it a little bit. Okay? So what I'm going to do is I'm going to move this theta, the magnitude of theta onto the right-hand side. So this is some constant and some magnitude, okay? And it's two parameters. And I'm just going to say, let that equal to 1. And that's not going to change the direction or the problem. Move this over here, magnitude of theta times c, and set it equal to 1. I could do that. This is not going to change this. And so, if I set it equal to c, then c is equal to what? Then c equals what? 1 over theta. Magnitude of 1 over theta. So that problem can be turned into maximize one over like that, subject to yi theta transpose xi plus theta naught greater than or equal to 1. Okay? Then what I'm going to do is say, oh, maximize the inverse of that. That is like minimizing theta. Such that functional margin greater than for all the data. To make that skip. No problem? Anybody? Questions? It's very easy to understand. Then, minimizing theta, the magnitude of theta. Magnitude, it's maybe a little bit difficult. Or I'm more at ease with something minimizing a quadratic. Instead of that, minimizing the magnitude, minimize the quadratic. How would this one be? How would you represent something like this in a vector form? Just theta transpose theta. That would be good. But representing that in terms of just theta, difficult because you have to do a square root, square, and then you have to do a square root. The square root comes in. And rather than working with square roots, I like just squares. I like quadratic equation. And I put a half there. Why do you think I put a half there?
So when you take...
If I take the derivative, then it goes away. And there it is. That's what you want to do. This is support vector machine. Okay? Minimize this, subject to that. Oh my goodness. How do you do this? We've seen something like this in regression. Huh? Minimize the square, and then we had ridge regression, then lasso type of thing. All of this. How do we do this? You want to set up, so I'm going to teach you how to do this. Lagrangian multiplier. Using Lagrangian multiplier. You have to set up a Lagrangian. Okay? And we'll be talking about this. Lagrangian here, so here it is, here's this equation. Here is this optimization problem. It's minimizing, what do we call this? This has a name. Objective function. And what is this? This is the constraint, right? And what do we call this whole thing? It's optimization problem. And what do we call this? This is, we'll say cost. This. Okay? Just some terminologies. Okay, now I want to, sorry, there's a typo. I'm going to put this thing together like that. How many constraints do I have, first of all? No? No, I have how many? I have n number train. I have n constraints. Okay? So here it is. The objective function comes down like that. And then the constraint comes down. Oh, and then I move this thing right over here. -1. Like that. And then I add in this thing called Lagrange multiplier. And how many multipliers do I have? N number. Okay. Oh, here it is. Lagrange multiplier. And this problem turns into a min-max problem. I'm minimizing with respect to theta naught and theta, right? And I'm maximizing with respect to the Lagrange multiplier. Okay? And the Lagrange multiplier here is assumed positive. Let's see. Do I have? Okay, now. So I'm going to skip a couple of slides because let me first explain how this works, and then explain this thing in more detail. So this constraint right over here. So that equation, that optimization problem turned into a min-max problem. Okay, like that. So, and this term has to be what? This term has to be 0 or positive, right? Non-negative value, right over here. Okay? And I want to minimize it. So let's assume I have an x. I have a theta, which makes this thing negative. Okay? Listen, okay, how this works. Makes this thing negative. So I got a negative here and a negative here. So which makes it what? Positive. What is alpha trying to do? What is alpha trying to do? It's trying to raise the value of this. So what is alpha going to do? If this is negative, positive, alpha, what is alpha going to do? Right here, what is this operation going to do? It's going to make alpha big. It's going to raise this, woo, very high. But sitting at the end is minimization of theta and theta naught. Do you think this theta and theta naught like this? That this is going up like that, raising it? Ooh, I don't like that. So what is theta and theta naught going to do? How? What is it going to do? it's going to make this such that this is positive or equal to 0. Right? Because it doesn't like alpha raising this value of this. So what is this going to do? It's going to satisfy the constraint. Do you understand what I'm saying? Sorry. Oh! So that's how the constraint is satisfied. We need to satisfy the constraint. By having the minimization at the end, it's going to satisfy this. Okay? Now let's say it's satisfied. Well, let's say it's satisfied. This leads to something. This is positive. What is this alpha going to do? It's trying to maximize this, but this is positive. It's because it's satisfied. And it's got a negative sign here. So this value is negative. Alpha wants to raise this value. So what is it going to do? It's going to make it 0. So for data, for values xi, where this is positive, this alpha I is going to be 0. If this value is 0, if it's 0, then alpha is going to be some non-zero value. It doesn't matter, right? So now I want to say this. Which of the xi's will make this equal to, will have this equal to 0? Which of the training data will make this thing equal to 0? Has it? Support vector. Now first of all, I want to say this. For each of the training data, xi, x1 through xn, there is a corresponding alpha. Right? For each of the data, there's the same number of alphas there, right? For the support vector, which makes this thing equal to 0, the alpha will be non-zero value. But all the other data, which will have this value positive, right? Because it's further away than the boundary, right? This will be greater than 0, right? Then alpha I will be what? Will be 0. You understand what I'm saying? So let's look at here. Let's go to this picture right here. Ooh, there is x1 through x1, 2, 3, 4, 5, 6, 7, 8, 9, and like that, right? All of these data will have functional margin greater than 1. They'll have value greater than 1, right? That one right over there. That one will have that term. This term will be greater than 0. So the corresponding alphas on these things, this one will have alpha, corresponding alpha 1, alpha 2, alpha 3, and so forth, alpha 4, and all of that, they will all be 0. But for these ones, alpha does not have to be 0. Alpha non-zero value. Non-zero positive value. Okay? Okay. So let me just go through this. Okay. Maybe I'll go through this slide here and then talk about that. Okay, let me just go through the slide, the way that the slide is, and then I'm going to talk about Lagrange multiplier. Okay, so we were trying to minimize the min-max problem of the Lagrangian, right? It turns out if the Lagrangian is differentiable, it's a nice behaving function, okay, and it's convex, then I could switch these two around. Okay, it's a mathematical, okay, so it's right here. Lagrange, who is Lagrange? He's a very famous French mathematician, philosopher, extraordinaire. You know. His grave is, by the way, in Paris. Anyways, he showed that you know, if that is convex, then you can switch that around. So now, okay, now let's do this. Minimizing this with respect to that. How do you do that? How do you minimize that with respect to that? You take the derivative. I'm doing this inner thing right here. And in that case, if I take the derivative, it leads to that. And it leads to that. Rather than doing the alpha here, minimize that. Just take the derivative and do that. So look at the solution for theta. What is theta equal to? Theta, which is the gradient, is equal to the sum of the data times its ground truth label, and I'm going to take a linear combination of that. That's how my gradient is. Okay? So of all the training data that I'm given, positive and negative, I'm going to take the weighted sum of that. Okay? And it also has to turn out that if I take the weighted sum of the label only, it has to equal to 0. That's the constraint of the alphas. Okay? So theta is equal to and instead of this Lagrangian is a function of what? Theta 0 and theta, right? Substitute that in terms of alphas, and I get that equation right there. Putting it into the Lagrangian. And this is what I do. And what do I have to do with respect to this Lagrangian? What do I have to do after this? I have to maximize with respect to alpha. Okay? Subject to alpha greater than 0, and that has to be satisfied. Okay? And you can ignore this perceptron business. Okay? Now, there are a couple of conditions that you have to satisfy. And I mentioned what support vectors are. Okay, support vectors are, oops, there's that equals to 1. Right? Theta naught is equal to that. And this, so the constraint has to be satisfied, right? The constraint, all the constraint. What was the constraint? yi theta xi, what is it, plus theta naught has to be greater than 1. That condition. I have to satisfy this condition also. Why is this? Why is this condition satisfied? If it's a support vector, then what is this value? If xi is a support vector, what is this value? 0, and alpha can be something. If this value is greater than 0, non-support vector, then this value is what? Positive. And alpha has to be what? 0. So this has to be satisfied always. That one, that one. And there's another one. And alpha I has had to be positive. And we call those KKT condition. Kuhn-Tucker condition. KKT, oh, I don't have it right. Condition. Okay, so that it has to satisfy that, and alpha i's have to be greater than 0. Okay, this is KKT condition. Okay, so the solution in the support vector depends on what? All the training data? Is it all the training data? No. Only on what? Only on support vector. Okay? It leads to a sparse solution. Okay? So, before deep learning came, this was the best performing classifier. It worked really, really well in the real world. Okay? Now I want to, so it's sparse representation, maximizing the margin, that led to minimizing the magnitude, and it somehow led to a simple hypothesis. Maximizing the margin. So whenever you have, we call this simple, if the margin is big, okay? And the generalization error related to this is proportional to the number of support vectors, and also the margin, and margin. Two things. Proportional to the number of support vectors and the margin. So you're going to, so what does this mean? So you're given training data, so you solve this optimization problem, you get your theta and theta naught, and if your margin is big, and the number of support vectors are small, then you're going to do well in the real world. Okay? Does that make sense? So now I want to go and talk about Lagrange multiplier. Okay, so this is something that you should know as an undergraduate, but maybe, I don't know, you forgot it or something, so it's very important, so I'm just going to go over it very quickly. Okay? Okay, here it goes. Oh, I have this maximize some function. And where's this? I need this one. Okay, maximum. I have this two cases. Okay, let's look at this first case. maximize that, and I want my constraint to be that. Okay, it's a very general form. Okay? It's a little bit different from what we did. We actually did this. Maximize this, and make gx greater or equal to 0. Oh, you said, oh no, we didn't do that. We had something like this. What are you talking about? We have this. How is this same as that? Of course it's the same thing. I just put that minus right here. With that. It's the same thing, right? So, before I talk about that, I'm going to be talking about that. Okay, let's look at this. Okay, assume that we're looking at this. Okay. Assume that X star is a solution such that this is true. And X star is also the maximizes fx. Okay? It's the argument that maximizes fx. Oh no. Okay. It's so this. I could write this as that. It's the same thing, right? This is the same thing. Now I want to consider gx equals 0. This is one particular sort of a contour. Okay, a contour, a contour plot of gx. I'm going to have gx equals minus 5 here, gx equals minus 4 here, and so forth. And so forth, right? And gx equals 1. This different contour. This is contour. Anyways, okay? Now I'm looking at a particular contour where gx equals 0. And I'm going to look at, I'm going to go along the gradient, along the contour. Then, so I look at this. Gx star, it's a point where it's equal to 0. I'm going to go delta x along the contour. And then I'm going to subtract the value of gx. What is this value going to be? This value and this value is going to be what? I'm going along the contour. So this value is equal to 0. This value is equal to 0. Right? That value is equal to 0, 0, 0. So, and if I use Taylor's series to represent this, it will be this equals that plus that times delta x. That's Taylor's series, right? So this value is equal to 0, right? So the gradient is gradient times going along the contour is equal to 0. What does that mean? What does that mean? The gradient is orthogonal to the contour. Do you understand what I'm saying? This means that this is that, right? Well, and this is obvious because this is going along the contour where it's not increasing. Delta x is not increasing along G. But this, what is this value right here? That's going increasing direction of gx. And they are perpendicular, right? Okay, so this is an obvious fact. Okay? And of course, you know, if x star makes this thing equal to 0, and it, I'm sorry. So x star makes this equal to 0, x star also is the maximum of maximizing this. So x star is also perpendicular to the gradient of fx. Why is that? Why is this? So I'm going in the same direction in the gx, okay, along the contour. And this is the gradient of fx. This will make it bigger. This will make it bigger. This will make fx bigger. And we know that f star is the maximum. If this is not true, that means that we can move such that fx will become bigger. This happens at x star, I'm saying. Okay, this happens at x star. This is at x star. So evaluating. If you don't understand, please say so. This is increase at x star. This is increasing, and this is going along the delta x. Now, if I go, which direction is delta x? Where is delta x, by the way? It's going along the gx. It has to stay in the gx, right? Right? It has to. This dx is going along the gx equals 0. That direction. If they are not orthogonal, that means I can move such that f can be bigger. But this is saying, because it's perpendicular, I cannot go in the along the gx equals 0 contour to make this thing fx bigger. Do you understand what I'm saying? That's what it's saying. So it turns out that what we have here is, so gx is equal to 0 right here. This is right here. So as I said in the first one, the gradient is perpendicular to the gx direction, right? That's what we said. Gx, the gradient, is perpendicular. And by the way, I should also show you where delta x is. Delta x is along this direction right here. Delta x is right along that direction. Delta x is along that direction, along the contour. So we said this is from 1. It's perpendicular. And we also said that the gradient of delta fx is perpendicular to this, to delta x. It's perpendicular to this contour. Okay? So both of them are perpendicular to delta x, so we have this kind of condition. Where I take the gradient of fx, gradient of delta is in the opposite. It could be in the opposite direction, it could be in the same direction. So I can write it like this. They're opposite or same direction, but they are proportional. What's the proportionality? Lambda. Okay. Lambda can be plus, it could be positive or negative. Do you understand what I'm saying? This is the constraint. So this combines the optimization, the objective function, and the constraint. And if I take the integral of this, what do I get? What do we call this? If I take the integral of this, what's the integral of this? It's Lagrangian. right? That's Lagrangian, okay? Now I'm going to look at the problem that we've been looking at. So we had, usually, I was trying to, put all of this thing in one space. So usually it would be like fx such that gx is greater than 0. This is an optimization problem that we often run into. So this was, in regression and with support vector machine and so forth, right? So how do we do this? Okay, there are two cases to consider. When there's two consider cases. This is case 1. This is case 2. What is this? What is called the constraint is not active. What does that mean? Oh, I'm trying to solve this without thinking about this. So how do I do this? I take the derivative and set it equal to 0. Huh? And it happened to be that maximum, the x star that make this maximum, or the gradient equals 0, satisfy the constraint. So what does this say? Hi. In this situation, the x star that maximizes this automatically satisfies the constraint. I don't need this. It's the same as just this one. And we call that, this case, the constraint inactive. Inactive situation. Okay? The other case is this. Maybe this figure gives you a better... Look at this picture right here. Here is a contour plot of f. So this is fx equals 1, fx equals 2, 3, 4, 5, and the maximum is right over here. Okay? Right over here. And gx, there's a contour. There's lots of contours for gx. But the gx, this is gx equals 0. Below that is gx equal minus 1, 2, 3, and 4. Gx positive 1, 2, and 3, and 4. So the maximum point of fx does not satisfy the constraint. Right? So where is the maximum point going to be? Where's the maximum point going to be? Where gx is equal to 0, at the boundary. Right? Because the constraint was gx, what is it? Gx greater or equal to 0. So it's right over here. Do you understand what I'm saying? 이해하고 있어요? 고개만 끄덕끄덕 알고 있는 거야 진짜? 어려워. It's not a difficult. What don't you understand? Let's look at this. This is a contour plot of fx, right? Fx equal 1, fx equal 2, 3, 4, 5, and the maximum point is here. I haven't drawn all the contour plots for gx. This is equal to gx equals 0. Then, going this way, I have gx equals 1, 2, and 3, and 4, and 5. It's positive right here. Below that, gx is negative. Okay? Gx is negative right here, down this way. What is my objective? I want to maximize fx, and I want my gx to be non-negative. So where is the solution? We're on which what is it? Gx. At which value of gx would the solution lie? Gx equals 0. The solution has to be here on gx equals 0. Yeah. Yeah, we're talking about. Okay, now. Okay, so right over here, okay? Now, we also know that the gradient of gx is what? Is perpendicular to the contour. We prove that. We go along delta x. Huh? Delta x is along the contour. There's no change in value. But what is this? What is gradient of g? It's always in the direction of increasing g, right? That increasing of g is going to be perpendicular to the direction of gx being the same value. Yeah. Okay. And I also proved that fx, the gradient of fx, has to be perpendicular to this. Why? If it's not, then I could move such that to make it increase. Do you understand what I'm saying? Okay, now here. The important thing is, okay, now the gradient of f and gradient of g are in alignment, like in this case, like this case. They're in alignment, right? The direction of gradient of g and gradient of f, in this case, has to be what? In the opposite direction. Okay? Meaning that delta f is somehow proportional to delta g. Okay? This direction and this direction have to be opposite. So lambda has to be what? If lambda is positive, it should be negative right there. If lambda, I could say lambda is positive. Put a negative sign there. Then what does it say? This direction and this direction are in opposite direction. Okay? So what does that mean? I can write it like that. I could put this thing right over here on this side and I could do that. But lambda has to be greater or equal to 0. Because they have to be going in opposite direction. Okay? So combining this active and inactive, I can write it like this. To represent inactive case, lambda equals 0. If it's active, this is, by the way, this is called the active. Lambda here is positive. Okay, so to combine this, for this problem, lambda, what's the constraint on this? Is either non-negative. Non-negative. Okay? And this is by the Kuhn-Tucker. Oh, there's 4 actually. This is the constraint. This is what the multiplier had to satisfy. This had to equal 0. This was like multiplier and the constraint, right? It's either. And then we had to solve this. This is the Kuhn-Tucker condition. Okay, so I want to skip all that because I'm running out of time. I already talked about this. The mechanism. But what I want to say, I'm going to skip all this. Oh. Yeah. I should be talking about this now. Soft SVM. Yeah, I explained. So, support vector machine. Lagrange multiplier. Now, I'm going to explain soft margin or soft margin SVM. The other one was called by the hard margin SVM. What is soft margin SVM? This is how I like to see it. I'm going to allow for some exception. I'm going to allow some training data to be inside the road. But I want to minimize the distance, the some distance away from where it should be. Okay, so like this guy right here. This blue. So these blues, these circle blues, this yellow is okay. It's a support vector. This blue is a support vector, okay. That's support vector. Hey, this one is not following direction. And I'm going to say, oh, this is about epsilon away from where it should be. This one is also epsilon. Okay, this one is away, let's say, epsilon 1 away. This one is epsilon 2 away from where it should be. But I'm going to allow that. I'm going to allow it, and I'm going to try to make the road wider. Okay? Anything outside, anything that's obeying, then the epsilons are all zero, correct. So here, what is the objective? I just want to skip some of these things. This is what I want to do. Look. Hey, look. This was what we saw before. I want to minimize this. Remember? Minimize this. And I want to obey this constraint. Right? But now in soft margin SVM, I want to minimize not only the margin, okay, but also the sum distance away from where it was. And I'm going to call these things, these are called slack, by the way. Call this slack. So for each of the training data, there is a slack. If it's on the right hand, if it's on the right side, if it's okay, what is the slack value? 0. If it's not obeying the condition, then it's going to be that distance. Okay? Do you understand what I'm saying? Ihanna? Do you understand what I'm saying? You want me to say it again? Okay. I'm going to define a slack for each of the training data. Okay, I'm going to define a slack for each of the training data. If the data is on the on the correct side, if it's obeying, then the slack is equal to 0. All the training data will have a slack. If it's on the edge, the slack is 0. If it's not obeying, if it's in the road, the distance, that positive distance, is called the slack. So each of the data has a slack. What are the slacks for this one? 0. If it's disobeying, it's that distance. Okay, I have 2 more minutes and then I'll just... And what is my objective? I want to minimize, this is the margin, right? The geometric margin, if you remember. I made C times the modulus of C equal to 1, and then I made C, C was the margin, right? Geometric margin, right? And C was inverse of the magnitude of the gradient, right? I want to maximize the inverse of the gradient, so it was minimize A of the in addition to that, I'm going to minimize the sum of the slacks. I want to minimize the overall wrong thing, okay? And I've changed my constraint. Before I made such that the functional margin had to be greater than or equal to 1. Now I'm making it 1 minus epsilon 1. Okay? Okay, so I'm going to be talking about this. Well, I should have finished this thing today, but I won't. I'm going to show you a very nice technique, very easy technique, where you don't have to do convex this Lagrange optimization. We're going to be doing gradient descent, and we will get the same solution. So I'll show you that, and then we'll move on to our next topic. Okay, any questions?